Well, welcome to this video which looks at generating the skill to write chemical formulas. Well, it goes way back to the periodic table which is in front of us here. The periodic table is structured to represent the way in which electrons are organized in terms of orbitals, and it is structured so that it's quickly and easily able to see what is its valency. Valency means the number of bonds it will form with other atoms. So let's go recap quickly. So here we have, for example, hydrogen, and it has a number 1. That reflects its atomic number, which is the number of protons, but also that is equal to its number of electrons. So hydrogen has a nucleus with 1 electron whizzing around. Helium has a nucleus with 2 electrons, and so on. So these are organized in a certain way. We also know that in Bohr's model we have number of shells. The first shell can have 2, the next shell can fill up with 8 electrons, and the third one with 8, and so on. So let's come back to something like sodium here. Sodium has 11 electrons, has first shell with 2, notice how the periodic table matches. Next shell has 8, so now we're up to 10, and we have 1 on the outer shell. It's called its valence electron. Now, well, the other principle is that everyone wants to look like these guys, and that is the noble gases, where they have a full outer shell and they're energetically very stable. And most of them in the early atoms that we're familiar with have an 8 in the outer shell, so sometimes that's referred to as the octet rule. So the aim is that the electron wants to react to become a stable arrangement of electrons, in a sense mirroring heliums, neons, argons, etc. So let's go back to sodium. Now sodium's on that row, it has 11, and we've worked out it has 2 in the first shell, 8 in the second, that's 10, and has 1 hanging out by itself. Well, that's very susceptible and it's very easy to react with. So it has a choice to either gain 7 to look like argon, not possible, or it can lose from its 11 1 to form neon. Well, that's what happens. And sodium loses, and through forming 1 chemical bond, it loses an electron, and from going from 11 to 10 to look like neon. So it said it reacts once. It's said to have its valency of 1. Now lithium is 3. It has 2 and 1. Similarly, it has 1 on the outer shell. Well, there's a choice to gain 7 again, look like neon, or it can lose 1 of its 3 to look like helium 2, which is a full outer shell and a stable state. Well, it loses 1. Similarly, all these have 1 out on their own. So they react once and have a valency of 1. Let's come across to magnesium now. And magnesium is 12. In a similar way, it will lose 2 electrons to look like neon. It will react twice. Beryllium has 4, and it will lose 2 electrons to look like helium. So it will react with 2 bonds, or it has a valency of 2. So all these have a valency of 2. Can you see how the periodic table is arranged very well? So column 1 has a valency of 1, column 2 has a valency of 2. Well, boron's 5, it can lose 3 to look like helium 2, or it can gain 5. Well, it's actually sometimes does both, but mostly it loses 3. So aluminium 13 can gain 5 to look like argon, or it can lose 3 and look like neon. Well, it loses 3 most of the time. So its valency in column 3, notice 1, 2, 3A or 3A there, it has a valency of 3. Well, the carbon, it's 6. Well, it can lose 4 to look like helium, or it can gain 4. Well, it's in the middle, so it does actually both. So it reacts 4 times. Silicon 14 to 18, or 14 back to 10. It reacts 4. So that column 4 has a valency of 4. Now this gets interesting. Nitrogen has 7. It can gain 3 or lose 5. Well, most of the time it gains 3. So it actually reacts 3 times. It actually takes 3 electrons to come 10. Phosphorus is 15, goes to 18, and so on. So this column is 3. Oxygen, 8. To get to 10, it gains 2. Sulfur, 16. To get to 18, it reacts twice, 2 times, and gaining an electron from each of those bonds. So it has a column of valency of 2. The fluorines, the chlorines, the bromines, etc., they're all 1 away from an electron. So they will actually react and form 1 bond, and they will take 1 electron. They have a valency of 1. And these guys, they don't react at all, so their valency is 0. So recap. This column, column 1, is valency of 1. This column is valency of 2. This is column 3 is 3. Column 4 is 4. And column 5 is 3, and column 6 is 2, and column 7 is 1, and column 8 is 0. So that is the basis of which we will then use the periodic table to quickly work out what a formula of a common compound might be. So let's start with one we're really familiar with. That's H2O. So hydrogen, okay, column 1, it's got a valency of 1. Oxygen's column 6, raised again to valency of 2. And it's on that basis that we then start to have that skill to create H2O. Have a look. Well, let's have a look. Hydrogen that we have here, it has a valency of 1. Oxygen has a valency of 2. Well, that means there's an exchange of electrons in a bond. Well, it's got to be balanced. If someone takes, someone gives back. So let's have a look at what's going to happen here. So the valency is 1. Therefore, to make that 2-or, you're going to need 2 of them. And you just need 1 of the oxygen. So what's the formula going to look like? H2 and O1. Well, we don't need to put the 1 there, H2O. Essentially what's happened is oxygen reacts with 1 hydrogen to take an electron, gaining 1. But it also needs 2, remember, so it will actually react with another one as well. And both of those hydrogens are given up 1, that's their valency, and oxygen has gained 1 and 1, total 2. Formula is H2 of those and O1. So that's a common way of doing things. Well, let's choose something else now. CO2. Well, what's that going to be? In the same way, what's its valency? Carbon, have a look at it, find it. Column 4, so its valency is 4. Oxygen, what is its valency? Whoops, I've already solved the problem. Valency is 2. So they've got to be balanced, so I need 2 lots. In other words, carbon reacts with 1 oxygen and gets the 2, but it needs 4, so it will react with 2 of them. So the formula is CO2. So that's the process. Then it starts with the atom, then working its valency, balancing its valency to create its formula, putting the atoms down, writing their valency, balancing the valency to that. So let's try something a little bit trickier. And that's the hardest one I can give you. And if we can solve this, we can solve anything. So let's try something. Let's go with aluminium and oxygen. And that's aluminium oxide. Well, what's its valency? Look at aluminium. What column? Column 3, so its valency is 3. What's oxygen? We just worked that out already. It's column 6. Its valency is 2. Well, 2s and 3s. What's common? What can we make that? Well, we've got to make it balanced. We have 3 and 2 don't seem to go. But if we made it 6, so 2 lots of 3 and 3 lots of 2. That's 6 all. So what's its formula of aluminium oxide? Well, it's aluminium 2O3. And that's a balanced chemical formula. Pretty sweet, isn't it? You reckon you're ready for more? Well, let's try something new. We're going to have a look at those middle group of atoms, the sometimes called the transition metals. Let's have a look. I've got them up on screen. And then we've got like the coppers, the magnesium, the zinc and the lead and the iron and so on. So let's have a look at those and how we can use those to calculate a chemical formula. Well, the ionic is equivalent to valency. So let's take something like calcium. It's column 2. Its valency is 2. This is 2 plus because it loses 2 electrons and subsequently has a plus charge. But the 2 is its valency. Zinc has a valency of 2. Lead has a valency of 2. Now look at iron. It has 2 or 3. So it's signified with iron 2 and iron 3 that are there. And here's all the other common ones that are there. Now this one's interesting. It's called nitrate. And nitrate is NO3. It's actually a cluster of atoms. It's a polyatomic ion. And so its overall has a -1 valency. And sulfate has a 2 valency. So you might have heard of copper sulfate and so on. So what's the copper sulfate's formula? What about calcium carbonate, which is the hard bit that makes rocks and things? What's its formula? What about other things, like say copper nitrate? Is that different to copper sulfate? So there, now we can use these formulas that are there to start to work out what we call more complex ways of generating a formula. So let's have a go at that. Well, let's choose that one, that copper sulfate. So let's have a look. Copper, Cu. Have a look at the iron sheet. Its valency is 2. Now, sulfate is SO4, and it operates as a group. What's its valency? Well, that's simple. It's 2. It's 2 minus, but it's 2 overall. Is that balanced? Yes, it is. So the formula is CuSO4. Well, that seems quite easy, doesn't it? Well, what about something else with sulfate? What about something like sodium sulfate? So let's write that over here. So let's compare it. So sodium, we know it's column 1, and sulfate, it's 2. So its valency is 1 for sodium, and sulfate's valency is 2. So how do we balance those? Just like that, we go 2. And that's a 1, isn't it? So that's 2 all. So the formula is sodium sulfate, like that. Pretty easy, isn't it? Should we go up one level? Let's go up one level. Let's stick with sulfate and see if we can go the tricky one, say aluminium sulfate. Let's try that. Aluminium and sulfate. So what's its valency? We know aluminium, we've done it before, it's column 3, it's 3, and sulfate is 2. There's our 6 again. So that's times 2, 2 lots of aluminium, and times 3, 3 lots of sulfate. So how do we write that? Well, it's aluminium 2, that's pretty easy, but SO4, do I go 3 lots of S3O12? No, we say to act as a group, so how do we signify that, which we put brackets around it? So that is 3, like so. Altogether, there is 3 sulfur. Altogether, there is 12 oxygen. But that's its formula. So again, it's writing the elements, or in this case, the polyatomic ions down, and then writing its valency, balancing, and then writing its formula. So let's choose another one from there. That's from our ion sheet. That nitrate, quite common in sort of God's creation. So let's have a look at something quite common. Let's say magnesium nitrate. Magnesium nitrate. So again, it's magnesium, Mg, and nitrate, NO3. Well, let's have a look at those valency. Where does magnesium hang out? Well, it hangs out in column 2. Its valency is 2. And nitrate, its valency is 1 negative. It's so ion, therefore it's 1. Well, it's a 2 and 1 again. So we need 2 all. So it would be Mg, and there's 2 lots of NO3. That means there's 1 magnesium atom, and there's 2 nitrogen and 6 oxygen altogether, but it's written as magnesium with 2 lots of NO3. Similarly, if we had something, say, let's go for iron 3 nitrate. 3 nitrate 1, it's a 3-1, it's like so. So we balance it all together. We have iron, this 1, and we've got 3 nitrates. I hope you're getting the hang of that. So it's using the same principle as many different ways, but the most complex you can really get is something like the 3s and 2s. So what about a tricky one? What about aluminium chloride? Now, it can actually be 2 varieties. It can actually be aluminium Cl3. Work that out. Does that seem to make sense? But sometimes it's in column 3. It actually can be more than one place. It can actually have an alternate formula as well. It can be more than one arrangement. You can ask for aluminium Cl5. So you can explain why it can be AlCl5. Hint goes back to the periodic table and those orbital structures. Have a go. Well, that finishes that unit little exercise in terms of balancing formulas to make what the compound would look like. So I have a worksheet and the homework and revision exercises. You'll find a whole worksheet and you can go for your life and have multiple opportunities to make formula balance and form what the compounds are. So hopefully you get used to that and familiar with that, and that will help you when you're writing chemical equations, that you'll get the formula right for each of the parts of the equation.